Hi, everyone. I'd like to start by thanking the organizers for the opportunity to speak in the nearly carbon-neutral geometric topology conference. And today I would like to talk about a piece of joint work with John Baldwin and Ty Littman, which shows that the Legendrian invariants in not Floer homology are effective in obstructing decomposable Lagrangian cobordisms. So in this talk, of course, I'll first give the definitions of the objects in question, Lagrangian cobordisms between Legendrian links, as well as the tools that we use, the grid invariants, and the context in which they live in, before stating the statement of the results and some examples. So this is in the contact geometry mini session, and so I'll assume a little bit of familiarity with contact structures and Legendrian links, in particular front diagrams, but not much beyond that. So let's first define Lagrangian cobordisms in R cross R3. So recall that R3, in R3, the standard contact structure is given by the contact one form alpha, the z minus y dx. And if you recall, a contact structure is a maximally non-integrable two-plane field. And here it's given by the kernel of alpha. And the link in R3, which we'll be calling lambda for Legendrian, is Legendrian if lambda is tangent to the contact structure. So in particular, it lies in the kernel of alpha. It satisfies the z minus y dx, which is where the rules for the front diagrams come from. So in this talk, we'll focus on the symplectization R cross R3, equipped with the two-form d of e to the t times alpha. In particular, in general, if you have a contact three manifold Y equipped with a contact one form alpha, you can consider R cross Y equipped with d of e to the t times alpha, and you can show that that is a symplectic form. That two form is a symplectic form, so you have a symplectic manifold, and that is called a symplectization, which gives the right context for us to talk about link cobordisms, in particular Legendrian link cobordisms. So without further ado, a Lagrangian cobordism, as defined by Chantraine, is an embedded Lagrangian submanifold inside the symplectization. In a second, I'll recall what it means for a submanifold to be Lagrangian, such that the two ends are really just cylindrical. So that means that if you are in the R direction, in the T direction, of course I should have mentioned that T here, e to the T is the first coordinates of R cross R3. So in the T direction, if you go far enough in the positive direction or in the negative direction, then it's just basically R cross, from that point, from some point onwards, it's just R cross the knot or link, the Legendrian link, lambda top, lambda bot. And the rest of the cobordism L, which is the middle part, is compact with boundary that matches up with the two ends. So now, what does it mean for a submanifold to be Lagrangian? If you recall, that means that the symplectic two form, d of e to the t times alpha, vanishes when restricted to L. So you know that this is 0 when restricted to L, but we can ask for something slightly stronger, which is that the primitive of this symplectic form, e to the t times alpha itself is exact, right? So it is df with some function f constant on the two ends, technical condition. Somehow the right condition for right notion of cobordism between Legendrian links is really exact Lagrangian cobordism. So we'll always assume things to be exact. So Lagrangian cobordisms have some properties, some of which are kind of unintuitive. So first of all, something that you sort of expect. if you have two links that are Legendrian links that are Legendrian isotopic, then there exists a Lagrangian concordance in between. Just like if you have two knots that are smoothly isotopic, then there is a Lagrangian in between. There is a concordance, smooth concordance in between. And here concordance just means a cobordism with genus G equals 0. So topologically, it's just a cylinder. Lagrangian concordances are automatically exact. You don't have to check for the exact condition. Now, the main takeaway I want introduce, highlight here, is that Lagrangian cobordisms are quite different from smooth cobordisms and concordances. So, for example, Chantraine proved that if you have two knots, two Legendrian knots at the top and bottom, and you have a Lagrangian cobordism in between, then the classical invariants, the rotation number R, and the Thurston-Benneken number TB satisfy these two equalities. Sorry, not inequalities, equalities. TB of Bott, TB of the, in particular, if you look at the TB equation, there's chi of L there, the Euler characteristic, which means that if you fix the two Legendrian knots at top and bottom, the genus of any Lagrangian cobordism in between, should one exist, is fixed. This is in stark contrast to the smooth category, where if you have a cobordism of genus G, then you have a cobordism of genus G plus 1 and G plus 2. You can just add, handles and tubes and whatever. But you cannot do that to Lagrangian cobordisms. So in particular, Lagrangian cobordisms cannot be inverted whenever you have genus, right? Because that gives a directionality. The TB equation gives restrictions on what the genus is, so you cannot just flip it because the TB equation would not hold anymore. Well, can you invert Lagrangian concordances? Chantraine tells us that, well, no, not in general. And so Lagrangian cobordism and concordance are not equivalence relations, unlike smooth cobordism and concordance. Now, in a different direction, I want to just mention that the notion of the cobordisms, Lagrangian cobordisms, can be generalized to a more general setting, from R cross R3 to cobordisms in a Weinstein cobordism. This has been done by Ekholm, Honda, Kaumann, and Eliashberg, Ganatra, Lazarev. Now, what are decomposable Lagrangian cobordisms? In some sense, they are the easiest Lagrangian cobordisms we can construct, right? So how do you construct a smooth cobordism? One way of thinking about a smooth cobordism is by decomposing into elementary pieces, saddles, births, deaths, and you try to do the same thing for Lagrangian cobordisms. So a Lagrangian cobordism is decomposable if it is a product of elementary cobordisms. Legendrian isotopy, births, and saddles. No deaths. So here are the if you want to like drawing front diagrams, here are the elementary cobordisms. There are the Legendrian randomizer moves that I've hidden, but it's also the Lagrangian birth, which is the appearance out of nowhere of a max TB unknot. And a saddle, a Lagrangian saddle, is one where you can put, this is often called a pinch move, because if you put your fingers here and you pinch, then you get the left-hand side. Now, there's a little bit of different conventions on what you call the bottom of the cobordism and the top of the cobordism. But so I chose, we chose this convention where Bott is the left-hand side here and top and is the right-hand side here. And well, it doesn't matter what you choose. The point is that the direction of arrows here, there's a directionality. You cannot go from the right-hand side to the left-hand side. For example, if you try to write down the model of an elementary Lagrangian depth, you cannot do it because you realize it is not Lagrangian. So in particular, there's no Lagrangian elementary Lagrangian depth. So a decomposable cobordism is exactly by one that you get by composing these. Now, Conway and Nyren-Tosen proved that at least in R cross R3, decomposable cobordisms are regular. The converse is unknown right now. Regular here means that is tangent. The cobordism is tangent to the Liouville vector field. So the thing you need to know is that regular cobordisms are all exact. And so every decomposable Lagrangian cobordism is exact in every and so the open question now is the converse, right? Is a Lagrangian is every exact Lagrangian cobordism decomposable? Now you can compare this question to the smooth category where you ask, is every smooth link cobordism decomposable? The answer there is obviously yes, right? But in the Lagrangian, in the Legendrian and Lagrangian context is wide open. In fact, it's one of the major problems in the field right now. Now I want to switch gears and talk about grid homology, which is where our tools are going to lie in. So grid homology is defined by Manolescu, Oshvat-Shaka, and Manolescu, Oshvat, Szabo-Thurston. Given a knot K, you find a grid diagram G, which is basically a combinatorial object from which you define a chain complex, which we call it grid complex GC of G. And essentially, it's a combinatorial version of link Floer homology. If you take the homology of GC of G, you get GH, which is grid homology. And it basically computes link Floer homology with some annoying tensor product on the right-hand side that we usually ignore. Now, if you account for the tensor product, then the rest, the HFK hat part is an invariant of the knot. And so we write GH hat for that part. And that is a knot invariant. Coming back to the context of Legendrian links, Oshvat, Szabo, Thurston showed that a grid diagram doesn't just encode a knot K, a smooth knot K, but it in fact encodes the front diagram of a Legendrian knot, lambda of G, which has smooth type M of K. We'll see why there's a M. M here means mirror. So you have smooth type, the mirror of K. We'll see in a second. Here's an example. So here's a grid diagram. A grid diagram is exactly just a grid, n by n grid, such that in each column and in each row, there's exactly one O and one X, and the O's and X don't coincide on the same square. And it encodes a knot or a link. And to get the link, you go from O to X horizontally and X to O. You connect O to X horizontally, you connect X to O vertically, with the convention that the vertical strands are always on top of the horizontal strands. So that's the knots that this grid diagram encodes. It's the knot 10-132. And coming back to the grid diagram, I want to tell you about the chain complex associated to the grid diagram. So here I'm showing you two generators of the grid diagram. All the blue dots together give you one generator. And all the hollow red circles together give you one generator. You could guess here that a generator is exactly a bunch of dots, such that there is exactly one on each vertical line and one on each horizontal line. Note that I should have mentioned that this is actually on the torus. So the top horizontal line is really the bottom line. The top and the leftmost is the rightmost. And in fact, these are circles. which is why I'm not drawing any dots on the top and the rightmost circles. So I've just shown you two of the generators. If you think about it, there are 12 factorial generators in this grid diagram. And now that you have the generators here, I'm going to tell you about the differential. And the differential counts empty rectangles. So whenever you have a rectangle, and the convention is to go from red to blue here, from top right, bottom left to top left, bottom right. So every time you have an empty rectangle like this, and here empty means that you do not have an O in it, you do not have an X in it, and you do not have a dot inside. Every time you have an empty rectangle, then X appears as a term in the differential of W. And of course, there are many other terms here, and you can try for yourself to find other terms. For example, here's another rectangle right there, which are, sum up all these terms, and that's the differential acting on W. So that's the grid complex. And of course, you take the homology, you get grid homology. Now, I want to mention how you get I want to talk about how you get a Legendrian knot out of a grid diagram. So again, this is the knot as before. Now, if we change all the crossings such that the horizontal strands are now on top of the vertical strands, and then we tilt our heads 45 degrees to the left, then this basically is a front diagram of a Legendrian link. Of course, you have to smooth these corners and make these corners cusps. If you're familiar with the grid with the front diagram, you should see immediately which ones are cusps and which ones are to be smoothed. That is a obvious, naturally a front diagram, so you get a Legendrian knot or link. I'm going to call this link lambda 1, Legendrian link lambda 1. And because we change all the crossings, lambda 1 has smooth type the mirror of K. Okay, so it has smooth type M of 10(1)32. Now I want to talk about the Legendrian grid invariants, which are going to live inside grid homology. How do we do that? Now, coming back to the grid, we have seen this blue dot before, the set of blue dots before, which is one generator. Now, this generator is somewhat special. It is gotten by taking the top right corner of each X. And it's special because I claim that there are no rectangles from it. So I remember our convention of what it means for a rectangle to be from some generator to some other generator. If you have a rectangle from it, then it has to, the rectangle will touch the bottom left of some particular dot, and in particular will contain an X. Well, you can't have that. And so that is not empty. That's not an empty rectangle. So the differential acting on the blue dot X plus is identically 0. So it's a cycle. Similarly, if you take the bottom left of each X and make that, and look at that generator, X minus, is also a cycle. And so what Obstruct, Szabo, and Thurston proved was that these two, the homology classes of these two cycles are invariants of the Legendrian link lambda. So in other words, if you have a sequence of grid moves that realizes some Legendrian isotopies or random moves, then the isomorphism, grid isomorphism for grid homology sends the homology class in question to the homology class in question. Now, unfortunately, the homology class is also called lambda, but they're lambda plus, lambda hat plus, lambda hat minus. I'm going to call them lambda plus and lambda minus. In Obstruct and Thurston, show that these invariants are effective. In particular, they can distinguish Legendrian knots of the same knot type here. For example, M10132 has two Legendrian representatives with the same classical invariants TB and R, so they cannot be distinguished by TB or R. But let's say lambda plus is 0 for one of them and non-zero for the other one, and so you can tell them apart. For example, here, well, to be concrete, this is lambda 1, as we've seen before, and to get lambda 2, you do something to the red box. Now, it looks like that other things have changed here as well, but in reality, that hasn't. If you stare closely at this, nothing has changed. It's just been moved up. But the red inside the red box, topologically still the same, right? We've just moved some crossings from the right-hand side here. Again, I'm tilting my head to the left-hand side here. This is akin to the Chekhov-Eliashberg twist knot trick, moving crossings around, and that changes the smooth. Sorry, that doesn't change the smooth type, but it changes the Legendrian type. And you can tell them apart by using either lambda plus here or lambda minus here. Now, I just want to mention that Baldwin, Velivic, and Verteschi show that the grid invariants, which are these lambda plus and minuses, is equivalent to the famous loss invariant in not-Floer homology. Loss here is called loss because it's defined by Liska, Obstruct, Sabo. And the loss invariants, so Baldwin, Velivic, and Verteschi show that they're equivalent whenever they're both defined. The loss invariants are defined with open books and more geometric, defined more geometric. Now, coming to the statement of our main result, suppose you have a decomposable Lagrangian cobordism from bottom to top in the symplectization, and if you suppose you find suppose you find grid diagrams for these Legendrian links, then there exists a homomorphism from top to bottom. This is contravariant that sends the grid invariants to the grid invariants. Well, how can we use this? Well, the obvious thing is that you cannot send something that's 0 to something that's non-zero. So if top is 0 and bottom is non-zero, then no luck. There's no decomposable Lagrangian cobordism between the two. Well, from bottom to top, because you could have the other way. And the proof of the theorem is by explicit construction. It's a diagrammatic combinatorial proof on grid diagrams on the saddles and death, and the death map. Why death? Well, a contravariant, if you have a birth and then you have a contravariant map, that's a death map. There are other similar results. First, there's a result by Gola and Juhas that shows that the loss invariant obstructs regular Lagrangian concordances in a more general setting, Weinstein cobordisms. And the map they showed is functorial. We expect our map also to be functorial, but we didn't prove it. In a different direction, Baldwin and Sivek showed that the monopole analog of the loss invariant obstructs Lagrangian concordances in the symplectization without any assumption on the decomposability or regularity of the Lagrangian cobordism or concordance. Of course, and they also show that the monopole loss invariant is actually equivalent to the Hegat-Floer loss invariant. So, we're talking about the same thing. Now, our result is the first one that shows that the loss invariant obstructs Lagrangian cobordisms of positive genus, because both the Gola-Juhas result and the Baldwin-Sivek results apply to Lagrangian concordances of genus 0. We also have examples where the loss invariants give obstructions where symplectic field theory, for example, the Chekhov-Eliashberg DGA does not, and of course, vice versa. Now, I want to give you two quick examples. The first example is, if we have lambda 1 and lambda 2 as before, here the TB and rotation numbers and also the grid invariants. there is no decomposable Lagrangian concordance from lambda 2 to lambda 1 because here lambda 2 is bot, lambda 1 is top. You cannot go from top to bot because top is 0 and bot is non-zero. That's obstructed by lambda plus. And lambda minus gives you the other direction. Now the first half of this statement, the lambda plus statement was originally proven by Gola and Juhas because they proved it for the loss invariant, which corresponds to the plus invariant, lambda plus invariant. Now, if you want an example with positive genus, it's actually similar to as before. You have the same thing, but you add, what we do is we add a twist here or a clasp by changing locally here. You get a different smooth type and nothing, you don't change anything else. It's just two crossings. You do this to lambda 1, you get lambda 1 prime. You do this to lambda 2, you get lambda 2 prime. And changing one of the new crossings reverts lambda I prime back to lambda I, because if you change this crossing, then randomize the 2, you get back the previous link. So that means that there is a smooth cobordism of genus 1 between the two smooth types. And you can compute the Thurston-Banneker numbers and rotation numbers. And turns out that whether you have the prime or not doesn't matter. The twist doesn't change the vanishing or non-vanishing of lambda plus and lambda minus. So the Thurston-Banneker number tells you that any Lagrangian cobordism from lambda I to lambda j prime has genus 1, but then there's no such thing because, as before, for example, the cobordism from lambda 2 to lambda 1 prime is obstructed by lambda plus, lambda 2 here, lambda 1 prime here. This is 0. You cannot send 0 to non-zero. And similarly for the other direction. And in summary, Lagrangian cobordisms are heavily restricted by TB and R, but these classical invariants are not complete. And we have grid invariants providing further obstructions for decomposable Lagrangian cobordisms in a symplectization. Now, two natural questions are whether grid homology satisfies naturality. And this is work in progress with Haofei Fan and Marco Marengon, and whether we can use this to in the context of Lagrangian cobordisms. I think Lenny Ng has some ideas about this. Another question is, of course, could the grid invariants provide an example of a non-decomposable Lagrangian cobordism? Maybe if you construct a cobordism and then obstruct a decomposable cobordism between the same knots, then you're done. I think that's hard. Thank you very much for your attention, and I will see you guys all very soon.